186 or
4 years.
27.
No, yeah, 5 years. And they kept asking, but they wouldn't let me. And so then they played cherries and nobody was like, so I went over 2 days later.
If there's one cable per video,
Right.
we can test it out. If I just it's some kind of
January 2022.
It's just a cable that has a USB.
Started the physics.
And so I did small business.
COVID kind of times.
80% of it was writing contracts.
They've just been meeting.
And then meeting with a lot of companies. And I love it. That's, then I retired and spent a couple of years with part-time. That's all I wanted. Just Kansas, the SBD. Kansas, I knew them. Right. I was talking. I got about 3 months. Get out of here. So I literally started, I left from my job for 2 years. And now I'm really ready to retire. They're coming.
Yeah, I'm not gonna hold you to it. I'll remember you.
I do.
At least you remember my face.
We didn't even know by accident. I didn't connect. Stacy's iPhone is too. You see, it's with your
Yeah.
Science degree.
But I have to like, once I see
Supervisor.
see their face.
But you smart, man.
Yeah.
Just doing.
Honestly, very little.
It's easy for us. She's on the team.
But I actually enjoyed that.
I'm playing the real childish now.
Oh, that's true. They're inviting you.
Yeah, no, a lot of people showed up. Believe it or not, cars.
Oh, I see what you said.
What time did you go?
Guys, I couldn't believe it. I heard I know that. That's Aaron.
We're all just.
Right now, I'm just one
And now,
Cisco.
There's a professor. There's points. And, it's. Really now. Freak out.
I went in there at base.
Yeah.
I was like, that actually is probably.
Does anyone sat in my chair?
Okay, so it's 7:30 and we're going to get started.
They should be. Or they
Everybody's ready.
They lost. But into the machine.
You just tell me what you do.
Well, that's a.
Dan, are you ready for a start meeting? Okay, we'll get started. Okay, welcome to the April meeting of the Johnson Space and Astronomical Society. Doug Hahn, the president. And before we get started, we'd like to greet anyone who this is your first time here and you're willing to actually admit it. So who is first time here? Right there. Oh, the fellow behind you. Right there. Yeah, you. What's your what's your name? How did you find out about us and what's your interest in astronomy?
My name is Octavio Fuentes, and I heard about you guys on Meetup, and I want to expand my mind. I want to learn new things. Why not?
Excellent. Yeah.
My name is Anna Silva. I'm a student at UHCL. I also work at NASA for KBR with the EDA suits. The way that I found out for astronomy, I was just trying to look for something in the area that was something that I could access. And I'm glad that it came here.
And where did you find it advertised?
I looked up UHCL astronomy, and then I also went to the Get Involved site.
Oh, excellent. Anybody else? First time here, right there.
I'm Trina, and it was at NASA's JSC announcements. It was listed in the events there.
Roundup.
And but the roundup for the topic looked pretty interesting.
Yeah. That's going to be a good one, I think. All right. Anybody else? First time here. You don't look familiar. Right there.
My name is Carlos. I found out about this in a Discord group thing. There was a message for this meeting.
Astronomical.
Think about this one.
It's an astronomy club.
Actually, you're not new.
I was just saying, they founded the Physics and Astronomy Club here.
Okay, excellent. Excellent. Anybody else? Okay, right here.
I'm Daniel. I don't speak English very well. I came from Brittany in France.
They are basically the Irish of France. The culture is very Irish. Their language, however, is closer to Welsh. He was a top nurse instructor, but he came back to his first love, farming. And he knows the sky. He knows the sky very well, trust me, because he had the good fortune of living in a place where we do not have much light pollution.
Excellent. Anybody else first time here that wants to admit it? I see a couple people I don't know. Maybe you guys don't want to tell us your names. That's okay. Okay. I think I know everybody else. All righty. Okay, here's our agenda for this meeting. And if you're online, if you want to submit some questions, you can submit them to the jscslive@gmail.com or submit them as a YouTube comment. And our pal Trevor Quinn here will gather those questions and he will give them to our presenters. And you guys, don't worry about the microphones here because the sound system actually picks up everybody in the room. So we don't have anybody at the microphone like we do or LPI. So that will work just fine, I hope. Okay. If you would like to get JCAS emails and you don't get them already, you can send an email to Ron at this email address here if you want to just get emails about the meetings, or you can send them to David at this email address here if you want to get all the emails. Or if you don't have a phone or something, take a picture of that. You can, there's some tear off tabs up there by the orange bucket, and you can tear off one of those, and that has the same email addresses on them. You can join our email distribution. So I feel like I'm forgetting something. Am I forgetting something?
No.
I don't know. I feel like I'm forgetting something. We do the same thing every time. Okay. Anyway, so for our presenters tonight, which is Bruce over there. Bruce, talking to you, buddy. Okay, so when you come up here, I got this mouse pointer. The mouse is a pointer. Okay, so this thing. So don't use a regular laser pointer. Use this deal so that so the online people can see what you're pointing at. If you point up there, they can't see it. And wait, we're not ready for you yet. And then you won't have a microphone for questions. Sorry, I didn't mean to confuse you, but here's our speaker. So I just wanted to show him this mouse pointer because sometimes people aren't paying attention to me when I'm up here, so I'll make sure you got it. Okay, now I'm going to talk about Bruce. So Dr. Bruce Pollard is our speaker tonight. I'm actually pretty excited about this presentation because I think it's pretty cool. In fact, that's why we have it here at Clear Lake, because we thought this would be something students in the physics and astronomy department would be interested in. And I'm still around, so I can find my glasses. light waves and their uses. Now, let me tell you a little bit about Bruce before he comes up here. There he is. Dr. Bruce Pollard is a 20-year veteran of the North Houston Astronomy Club, having held many positions, including currently being president of the group. Bruce grew up in Wisconsin and got his PhD at the University of Florida in chemistry, specializing in design and automation of atomic spectrometers. He taught analytic chemistry at Marquette University for 8 years and spent 25 years helping chemical companies use computers and automation to research and improve their processes and preserve the environment. Now retired, Dr. Pollard consults for ship channel chemical companies and not-for-profit service groups. He helps share the sky with others by facilitating observations at the Insperity and Georgia observatories. His research interest is expanding the single-channel signals and noise studies that were part of his thesis 45 years ago to the camera detectors of millions of channels we use today for astronomical studies. So with that, is there a problem, Trevor?
Saying there's a problem with the main speaker.
There's a problem with the main speaker. And that seems to be coming through. Is it coming through on the stream?
Yeah, it's coming through on the stream.
All right, don't worry about it.
It's coming through here.
Okay, with that, let's welcome Dr. Bruce Pollard.
Well, it's fun to come here.
Yes. Oh, Bruce, you pretty much got to stand here.
Oh, yeah, that's great.
So the guys on the stream can hear you. If you move off over here, nobody can hear you.
Okay, great. Well, it's good to come here. After lunch, I can get my 2 books. Get my assistant. It's 100. We got some Frankenstein. Never mind that. I have done different kinds of spectroscopy, which is, looking at colors of light and what they have to do with chemistry and sorting them out for a lot of years. And I always did them in a very traditional fashion, which is using essentially a prism to break them into a spectrum. But there are other ways of breaking things into a spectrum. And there are a lot of different kinds of instrumentation that can be used for different things that we don't normally use past the telescope. And so I thought I'd just introduce them a little bit to you. I'm not going to go into the math. There are books that are focusing on interferometry and the math behind it. How many people here did a Fourier transform today? Maybe almost everybody, because your phone actually probably does a Fourier transform to take the noise out. But we're not going to talk about, we're just going to touch on Fourier transform a moment, because it's a way that you can transform from one domain that's related to wavelength to another domain that's related to space. So if you can vary the space, you can vary the wavelength. All you have to do is do the math in between, and that's called the Fourier transform. So we won't talk in depth about that. We'll just mention it along the way. What got me started on this is my brother, who's 6 years older than me and got his PhD at Cal Berkeley, has this sitting on his shelf. And it's Light Waves and Their Uses by Albert Michelson. And I don't know how many people we have some professors in here. So professors, if they profess for their whole time and then retire, a lot of places, they're expected to write a kind of a finishing treatise on everything that they learned, and then they get their retirement fund. Some of my friends who graduated at the same time that I did, they're all putting out their memoirs now because then they can get their retirement. And this is Albert Michelson's. And so I'm going to tell you a little bit about him. I'm going to make this thing work.
You can use the down arrow on the keyboard.
Sweet. So here's that book in bigger. And so here's my agenda. It's a story in 4 parts. I'm going to tell you a little bit about Albert Michelson, his biography. I'm going to do a brief history of light. So some people work with light every day, and this is going to be, oh yeah, I know that. Other people, if you haven't really ever studied the history of life, it's interesting because it started out as looking from me to you, and light traveling from me to you, to being waves, and lots of things in between in jumps of time, the way evolution and the way science works. We'll talk about the speed of light a little bit, because that's really what interested Michelson. He was a sailor part of the time, and when he was out sailing, he wanted to figure out which way light was going and how fast. And at the time, they thought it was going different speeds in different directions. Then I'm going to talk about the interferometer. That's the instrument that he basically invented. And some of the applications, very briefly, about light speed measurement, about distance measurement, about holography, about spectrometry, which is my space, and about astronomy, which is everybody here. So we'll spend more time talking a little bit about that. So here's Michelson. I was always going to dress up like him, but I don't have his hair. His mustache. He was born in 1852 in Poland, and he died in 1931. And he got his education at the Naval Academy after his family moved to the United States. And then he went back to Germany, France, and then eventually he was a teacher at Case Western, and then Clark University and the University of Chicago. He had 2 wives and 4 or 5 children, some of which became scientists too. And he was the president of the National Academy of Science from 1923 to 1927, which is, I mean, that might be as high as you can get in the non-political science space. Now it's probably maybe more political. And he got a lot of awards. He was the first American ever to get a Nobel Prize in the sciences for his spectroscopic and meteorological investigations. So that's Michael's. Oh, and his passion was light and its speed. So here's the brief history of light. We'll start back in 400 BC, and there's kind of a timeline along the side so you can gauge things. So there's Plato, and he advanced that light consisted of rays emitted from the eye. And the striking of rays of the object allows the viewer to perceive things as the color and shape and size of the objects. This is the essence of the extramission theory of light that would be influential for 1,000 years until Alzheimer, who was he could conclusively prove it wrong. Ptolemy wrote Optics, in which he discussed the theory of vision, reflection, refraction, optical illusions. Like Euclid and Hero and Ptolemy championed the extramission theory of light vision. So it's all to the eye. So the Islam academics contributed knowledge about light traveling in straight lines, focusing, and an early version of Snell's law. Snell's law is the law that we use when light goes through 2 different substances and seems to be bent to a normal, and we believe the speed of the waves change. And it's an ratio, the amount of change that takes place is in a ratio to the speed change that takes place. So Copernicus, I put Copernicus at the top because he really got things started. He proposed a heliocentric model of the solar system, a system in which the sun was held at rest, and all the planets, including the Earth, circled around it. Descartes, that's 1625, used a tennis ball analogy to derive the laws of reflection and refraction of light. the credit of the discovery of the law of refraction is given to Snellis, who derived it using trigonometric methods. That's what gives you the speed change. Fermat argued that light rays going from one point to another in the same region takes the shortest time. That seems straight lines the shortest. That seems obvious, right? But 1625. So then there's Newton. Newton did a lot of stuff. I guess probably for me, he's most famous because he sorted gravity. What about other people? What's famous about Newton for them?
Calculus? Calculus?
And his laws. Yeah. Let's see, then there's Huygens, who's Dutch, so suggested a wave picture of light. He really got that started. Crucial to his wave theory was a result recently obtained that the speed of light is finite. So then there's Young, conclusively demonstrated the wave nature of light through his double slit experiment. And I brought my little optical bench. The interesting thing is today, with the equipment that we have, you can do lots of experiments easy that took a lot of work for them to do back then, because they didn't have lasers. They didn't have photographic detectors with 4,000 by 3,000 pixels in them. So they had to build things and design them, and the kinds of movements required are micrometers to be able to move through the different wavelengths of light. And so you have to give it to them all the way along. And Fresnel was another guy. In fact, how many people have Fresnel lenses in their eyes now? It's a special lens that they're now putting intraocular that gives you a variety of focal lengths rather than just having to have glasses. The trade-off is that there's some extra formation of objects in it. But some people get it. Most astronomers won't get it because they want to see clear when they look through their telescopes. Kirchhoff. So we study a lot about the temperatures of stars, and Kirchhoff, he introduced the idea of the black body, and eventually Planck worked out the equation for it. So we think of how the continuous light from various temperature objects come from. And in between, in 1889, Michelson and Morley, that's when they introduced an object that used the inference pattern of Young and employed it with Morley to demonstrate the speed of light was the same in all directions with respect to Earth. This is interesting because they didn't know what was out in space. They thought it was something called the ether. And it conducted light and things through it. But the experiments that they did, where they looked at light from different angles on the Earth at different times of the year, and it was always the same speed, it made up the idea that there's nothing out there that is controlling the speed of light. Okay, well, so Einstein gets a whole page. He did special relativity. The laws of physics don't change even for objects moving in inertial frames of reference. But at the same time that everything had to be a wave, he got the Nobel Prize. Not for that, he got the Nobel Prize for the photoelectric effect, which proves that light, photons of light have physical nature to them to some extent. We talk a little bit about interference and diffraction experiments that required wave, and on the other hand, there's photoelectric effect. So it's two things. And when you study spectroscopy, as you go to harder and harder, we call them wavelengths, to shorter wavelengths, it becomes more of a particle like nature. I have to look back because I missed one. Here, I'll mix that guy. So 1865 and this Maxwell equations, and probably, I don't know how many people would agree with me, but probably Maxwell's equations are much more important than what Einstein put together. We live, all the stuff that we do and everything that works, how it works, is all based upon things being conducted from one spot to the next in ways the Maxwell's equations predict that light something will be at a maximum limit. Turns out that light is at that limit. And so again, I mean, there's a whole book, the electrostatics book, or the electrodynamics book, I guess it is, in physics, that it's just basically, it's the whole thing, Maxwell equations, pretty much. Hertz, description of light is electromagnetic waves. So he was pushing there, and it was looking as though, but nobody really came down to it at the end. Probably Einstein assigned the duality to a particular entity, and he called it the photon. So here's a few other things to get us up to almost time. Thomson performed experiments that clearly indicated the existence of negative charged particles, the basis of electricity. That was the electron 130 years ago only. Then Dirac really developed the quantum mechanics that we do now. And Towns I put in because he developed the laser, which really showed that that energy levels behave differently when you put more energy into a level above it than lower. Normally, most of the energy is in the lowest level, and then it's populated up by energy equations. But if you invert it, then the light behaves totally differently. The energy given off behaves totally differently when you shine a light of this energy down. You get not one photon back, but you get two. And that's the basis for the laser. I'll talk about the speed of light a little bit. We pretty much know, everybody's pretty much comfortable. It's a constant in vacuum. That's derived by Maxwell, not directly, but and it's much better measured than derived from the other things that we try to derive it. It's written down there. It's slower by the index of refraction. So in air, so we got 3 times 10 to the 8th. So in air, 2.25. In water, it's 2/3. In glass, it's about 2/3. And the other thing that everybody knows, I think, or should know in astronomy, is that the index of refraction of things is a function of wavelength. And what that creates is chromatic aberration. And that's why you can't make a single lens for your telescope out of one glass. You need several glasses so they kind of correct for each other. We've got a Takahashi at the observatory that has 3 kinds of glass in its primary objective. Galileo tried to measure the speed of light by having a servant take a lantern to a distant hilltop. Galileo was going to open his lantern, and as soon as the servant saw the light, he was going to open his lantern. When Galileo saw the servant's lantern open it, then he started counting. Well, he concluded that it was very fast. Grover was better. He used geometry and the movement of planets. And he came pretty close. He got 200,000 kilometers per second, and we know it's, what, 300 now? 188, right? What's it, 186? So here we are. Here's the history of all the measurements. Galileo all the way through to what we've measured now. And the speed of light in its measurement in a vacuum is so accurate, we use it to define other things. For example, a certain number of waves of a certain element emission are used to define what is 1 meter today. And down at the bottom, there's this little thing, wavelength time frequency equals the speed of light. So, interferometry and applications. Michelson's definition is an interferometer is any device which is arranged to separate or collect separated beams of light and allows them to reunite to produce an interference pattern. So, when I was a little kid, I used to love watching, sit in the tub and love making waves back and forth. See the waves hitting the wall. That I could make them bigger and bigger and bigger, stand the wave, and pretty soon there'd be more water out of the tub than in the tub. That'd be cool. But at the same time, if you drop two things in at the same time into a pool of water, you see the water move out, and you see lines where the waves are intersecting with each other. And that's really what interference is. So here's the picture. Here. So you start with a light source, and this is Young's double slit experiment. And I can show you that tonight. I brought my little laser bench, and the light goes through from a single wave front, goes through these two at the same time, and then they spread out in a wave, and so the waves intersect with each other. And you get a pattern, which you can look at, and at the same time, you can take your camera and collect the signal, and have the signal. And if you nowadays you can actually just use Excel, and you can take the data from your camera and you can put it into Excel, and Excel has something called Fourier transform function in it, and you can click that. And it'll come back with a different kind of graph, which is related to the wavelength. So there's this experiment. And this is the kind of image that you see bright in the middle and not so bright on the outside. And the interesting thing is, as the slit difference between here and here gets smaller, the distance between these gets bigger. And that's a wave. Math. Here's the instrument that he actually used. So it's a little tricky to do this because you've got to line up everything just right, and you have to get the right wave fronts to interact with each other. You can't just pick any ones. And so to do that, you start with here's your source, and it could be a star, or it could be a laser going through a pin, and then it goes through a beam splitter that splits the beam, and the light goes this way and this way, and then reflects and comes back. And if you have exactly the same path between this direction and this direction, then it will be a zero signal. The two light beams will interfere with each other and you get zero signal. If you just point it there, you see a nice little dot, and you see the hides. The other thing is that Michelson figured out is you couldn't just have one. You needed a second compensator, so the paths that the light took in each direction was through the same components. Because remember, the speed of light changes here and here. So if you didn't have here, the speed of light, you wouldn't have the same distance. And the whole object of this is to hold everything constant. And as you change the interferometer around, if this pattern changes, they measured this very carefully. They counted out 5,000 of these fringes and tried to measure some portion of them so they could measure the accuracy of one part in 100,000. And it's all physically. I'll show you a picture of the kinds of machines they used in a bit. So these are the two. This is the configured. The hypothesis was that the ether affects the speed of light. They always make a good hypothesis. Its conclusion was no. They couldn't see any difference in any way that they pointed the interferometer looking at any objects. A few other things that you can use an interferometer for. How many people have put a layer of oil and water and looked at the fringes that you get? Well, you can count those fringes, and using the same equations that we could use to calculate the distance between between the slits, you can get that distance. So if you know that distance because you know the wavelength, you know the speed of light, and you know the distance from it, then you can calculate that distance. And it can be very, very small, much smaller than you can measure with a physical instrument. And you can tell the shape when it's not lined up properly. And lots of times they'll actually put an interferometer on the side of a machine just to measure the fringes go past and to actually take that as the measuring system of the machinery. Lots of other applications, little ones. We have any other chemistry people here? One of the things they found that they could do is they could measure the index of refraction of all sorts of things by just zeroing the two mirrors out and then putting the glass cell in place. So that could measure that index of refraction. How many people have made a hologram? That's it's actually an easy thing to do. I did it in 1972. The physics professor at Carroll College, where I went to undergraduate school, had a laser and a couple of mirrors, and you just line the mirrors up in such a way that you have the laser coming in, you split the beam here, and you shine the light to a mirror, to a photographic plate, and then you shine the other light here, and it comes here. So you got now two paths, and when you split the light and do two paths, what are you going to get? Interference. Interference based upon path differences, right? So whatever you see along here, there's going to be path differences. I brought this along. I don't have the light. See if you can see it. See those worlds? That's what a hologram. Once you develop this photographic plate, that's what it looks like. But don't have it. But if you illuminate it with light all coming in the same direction, like from a laser that's been spread out a little bit from a beam, you can actually look in and you can see the object. And you can move from one side to the other side, and because you're changing your path, the hologram moves. So that's an exciting thing. It's taken lots of different ways, but in the end, it comes back down to looking at light changing its path a little bit. I told you about spectrometry. The big thing there is a thing called the Fourier transform spectrometer. You can do a broadband source, or you can do an atomic one. And it goes through a sample, and then you measure this. And instead of measuring the path difference, you vary the path, and you get the signal through the sample, and it looks like this. But if you do a Fourier transform of it, it looks like this. Here's the first, one of the first interferometers built, and this is the instrument that they use to count the fringes. So in the old days, I used to count 1 million photons with my photon counter. When I got my PhD, and it was no problem, I sat there and drank coffee. And these guys sat there and counted. So the magic of the Fourier transform, we just started.
Bruce, I got a question for you.
Yeah, go ahead.
Can you back up one slide?
I can.
Can you tell us a little bit about how that thing works? How did that count photons?
So this didn't count photons. What this did was count fringes.
Count fringes. Okay, how did this machine do that?
So the light came through and it hit something back here and it scribbled it on the paper.
Okay, I guess.
Pretty simple.
All right.
But the object was to count them all. There's great stuff on the web about Fourier transforms. So if you ever want to see the magic of it, you can start out with a signal as a function of time or space, and by doing a Fourier transform, convert it to a signal as a function of frequency. Signal as a function of frequency is a spectrum. That's the instrument that you might buy today. That's a Fourier transform spectrometer. Okay, so interferometry in astronomy. You can use it to resolve bright objects at a distance. In fact, that's what Michelson did. You can use it to stellar size. You can do high resolution spectrometry. The infrared, the Fourier transform spectrometer is perhaps the most, it's the second most high resolution way of resolving spectrometers. Now they use a different kind of interferometer called a net shell, which is a different kind of grading. It's used a lot to multiple mirror systems. Any place where they have a bunch of mirrors that they're aligning, for example, up in space, there are lasers which are set to measure and align based upon those fringes. They're used to stabilize images. How many people have been reading or looking up about speckle imaging at all? If you want to get better signal to noise with your camera than just stacking, you have to take the best images from your pixels and just use those to add them together. Each of those best images is called a speckle. And so you can add those together and then you can convert them, not to a Fourier transform, but a different kind of transform related to Fourier that gives you a higher resolution picture. Exoplanets, if you can resolve things better, then you can do exoplanets. And they're used in all wavelength ranges. The first spot that this was mostly used was in radio. And in fact, the interferometry in radio is how they're looking at black holes today. Imaging black holes. Everybody saw the picture of the orange picture. That's an interferogram. A little bit about telescopes. How many people, everybody, or many people know that the resolution capability, the ability to tell two things apart in their telescope, is determined by usually the primary or the secondary, whichever is subtending the least light. So the primary, usually the primary is you can't make it any bigger, so and then you can make a secondary bigger. So the primary is what determines it. And so you want to be able to tell the difference. Is this one thing or two? And the other thing that you see here is this is a star in a telescope. Can you see this? What do those look like?
Please.
Fringes. It's the same thing that we talked about. It's an interference pattern. So your telescope, every object that you're looking at in your telescope is really an interference pattern determined by the size of your primary objective. And for people who aren't diehard astronomers, the thing that we're always interested in is collecting a small solid angle. So a circle has 360 degrees, right? So if you take that circle and divide it into degrees, you get a degree. And then what do? You break that down into minutes and then seconds. And then if it's not just 2 dimensions, if it's 3 dimensions, we put the word arc in front of it. So an arc second is a 360th of a sphere. So, and not an arc second would be an arc degree would be a 360th. An arc second would be what, 3,600 times 24. So anyway, it gets pretty small. So there's actually a simple equation that you can get to figure out what the resolution of your telescope is. It's called the Dawes limit. And it's a limit because with the atmosphere that we deal with, thank heavens we've got it so we can breathe and it rains and everything. The atmosphere is not stable. So very few telescopes actually operate at the Dawes limit. But a fun thing to do is to look at, to use your telescope and to look at double stars and see which ones you can resolve. And then remember what the best day you can resolve them and how close to the Dawes limit. When you buy a telescope, that's one of the specs, it's the Dawes limit. So 4-inch is 1.14 arc seconds. A 12-inch is 0.38. So here's 118-inch. Anybody know where there's a 118-inch mirror?
West Texas?
No.
Oh, well, that's.
So the Hubble has 0.037 arc seconds. Polaris A and B, Polaris is a double star, are separated by 18 arc seconds. So all of these things should be able to resolve Polaris. So regardless of what telescope you've got, see if you can see Polaris and its cup. So Michelson went and he said, so I'm going to build a Michelson interferometer out of a telescope. And what he did was he collected the light from 2 paths from a star, mixed them together, and then mixed them together to get to go into the telescope and to get an interference pattern. And the interference pattern we use to mathematically design the size of something. You'll see when you look, if you have time to look at it, you can measure the size of something. You can tell whether, by looking at the interference pattern, you can tell whether it's one thing or two. And one thing or two is what you want, because that's resolution. This is the kind of system that you have. Some of these pictures are right in this book, and this is you can get this on the web now. I think the whole thing is published there. What he did was he took two different slits and put them across and brought them onto the main mirror, and then he used them to calculate the distance. It's tricky. I didn't know totally what was involved with it until somebody heard me give this talk and he said, "You need to study this book." And this book gives away a lot and spends lots of time, so it gives me a chance to fix up my little optical bench to make it work with my telescopes that I've got. So, two telescope interferometers are not uncommon. So you have the two telescopes that collect the signal, and sometimes they just use an optical path, and they adjust the optical path again. The paths have to be exactly equal. In the radio systems that they use now, they record all with an atomic clock that measures the exact time that everything's signals are coming in, and then they deconvolve that with a fancy computer. I use the fancy word deconvolve. That's when when you perform math, go from one domain to another. Oh, so here's this is the VLTI, very large, and it's 8 meters, and then it has all of the things connected together. The interesting thing here is its resolution is plus or minus 0.08 milliarc seconds. So remember, the Hubble is 37 milliarc seconds. So this is another 1,000 times the resolution. You can do the same thing as I said. And there are great books and articles about this particular image, which is really a reconstructive interferogram of many radio telescopes all combining to make a telescope the size of half the size of the Earth. Radio telescope. I talked about speckle interferometry. It's a whole other help. And there are people who are doing a little bit of this to enhance their images. But a good example is this, the one of Jupiter down below. And the ability to resolve two things, shows the resolution of two things out of this. And I put, these are starting links I put throughout everything. So if you're interested in reading a little bit more about these things, you can. This is the book that I got. That it turns out the guy who actually done a lot of this stuff called me up and he said, "Well, I heard you talk. It's interesting. Did you know that you really do need that compensator plate in there for it to work? Otherwise, your path lengths are going to have to be a half mile long." I went, "Oh, okay." So you learn a lot, and it's an interesting thing. So thank you very much. Any questions? Where are we time-wise?
Oh, you're good.
So I don't want to interrupt your meeting too much. Oh, go ahead. Yep.
You mentioned interference patterns with radio and X-rays and light. Do we do gamma ray?
Yes. In
Okay.
fact, that's how it started. Gamma ray. That's the X-ray spectrometer works by seeing the interference pattern of gamma rays going through crystals.
Okay, because I think that would be harder than standard visual stuff because it's such short wavelengths.
Yeah, it is. you need a different kind of detector. You need a gallium arsenide detector with and we've done marvels with that. You know, Marie Curie would be alive today if we had a detector like that instead of her holding the thing up next to her.
Okay, yeah, the speckle interferometry, is that done with it says short exposure image, is that done with a regular image or is it done with an interferogram?
It's done with it can be done with a regular image, and there's available software from the same guys that bring you the stacking software. And the key is that instead of taking a long exposure, you take thousands of short ones and select the best ones and sum those.
Okay, we'll have to find out about that.
Yeah.
So that's a good one on me. Jerry,
But you're already doing it. You're already stacking a lot of pictures.
Well, stacking, the problem with stacking is that you can just get so far because
You're adding noise.
the noise from the sky, from our atmosphere, determines what the signal to noise ratio is going to be the best. So if you plot your signal to noise, as the signal goes up, it'll just reach some number and it'll just stay there. So you have to find ways of dealing with this, and the way that you deal with it is adaptive optics. They shoot a laser into the sky, and they measure the distortion of that energy, and then they link that to the signal coming in with an amplifier called, in short, we call it a lock-in amplifier, which increases the Q, the multiplication factor, the sensitivity greatly.
Okay, yeah, that's a new one on me. I'll have to look into that.
Yeah, but that, if you're after digging images out that are the real thing, speckle interferometry is the best you can do on Earth.
Okay, we'll do it.
And I brought an example. After you guys finish, I can sit down here for a while. I got a laser and I can show you some Young's things. And then also, the other thing is that if you, instead of having two slits, if you have 1,000 per millimeter, per couple millimeters, you have a grading. And that's what we use to do spectroscopy now. Thanks.
Okay, thank you very much for that, Bruce. And at the end of the meeting, we will go over here and you guys can take a look at Bruce's optical bench that he brought with us. Do that for a while before we take off to go to Monty for you. That would be interesting to have that demonstration in RV. Okay, so Ron, are you here? That's Ron. Did you want to say anything about the DVD library?
Yeah, I'm gonna bring it to the next meeting. I did something last week that needed to be done 10 years ago, and that was to reconstruct the whole thing. There's well over 200 DVDs now, so that have been donated. And the majority of them, 80% maybe, are the ones that you see there are the, in fact, for Astronomy magazine. So they're really good. They're about 45 minutes long, so got plenty. So I'll bring it to the next time.
Okay, so next meeting. All right, good. Okay, so the meeting, after the meeting, after we get done here, for all you new people who have been here for, we're going to go up to Mod Pizza and we can get together and talk about astronomy and other related topics. The Mod Pizza we go to, you shoot up Middle Brick, go north, and you take a left to Clear City Boulevard, past Colorado, and right in front of HEB, there's a Mod Pizza, and we'll all get together there afterwards and continue our meeting after the meeting. All right. Now, normally we take a break, but since we only have a couple things left on our agenda tonight, I'm not going to take a break this time. But I am going to do something different. Okay, so we've been using this slide here for our break slide for I don't know, a little while. And I'm aware that there's some people are wondering about this image, so I'm going to tell you a little bit about this instead of just put it up here. Okay, so this image is called the Rho Ophiuchi area, and it's named after this triple star over here, Rho Ophiuchi. So you look here, this is one of the most colorful areas of the sky. So when you're doing astrophotography, you're looking for something that's got a lot of color in it. This is it. This is one of the areas that has most different colors and things in it, most interesting objects. So Rho Ophiuchi looks like a triple star here, but it actually is 5 stars. 2 of these are actually doubles. So you know it looks like triples. It's actually it's 5 there. And this one is about 360 light years away from us. So around Rho Ophiuchi, there's this blue reflection nebula, which is IC 4604. And there's 2 other blue reflection nebula. There's this one here, I-4603, and this one down here, I-4605. So 3 blue reflection nebula. And most reflection nebula are usually blue, at least the ones that I've seen and the one I've seen pictures of. But there are also sometimes there are other color reflection nebula. This big gigantic yellow thing down here is another reflection nebula, but it's yellow instead of blue. So this yellow reflection nebula is Vandenberg 107 right here. In addition to the reflection nebula, there's actually 2 dark nebula. There's Barnard 45 over here and Barnard 44 down here. 2 dark nebula. And within this image, there's 3 globular clusters. Does anybody know what that one is by chance? I know if Jim was here, you know what that one is.
Messier 4?
That's it. Who said that?
I did.
Excellent. Oh, Justin knew. Okay, that's right. That's M4. It's a whopper. I mean, it's a big globular cluster. So there's this one here, and then right down here, the small one, this NGC 6144 right here. And up here, right up to the top here, this is M80. So we've got 3 globular clusters in this picture. And then this star down here, this is Antares. So Antares is a really big bright star in Scorpius. And it's called Antares, which means the rival of Mars. And the reason it's called this is because when you go out and look at Antares at night in the night sky, you look at it, at first you think it may be Mars, but actually it's too low in the sky to be Mars. But the way it looks, because it's so red, it actually looks a lot like Mars. Antares means rival of Mars. But what's interesting here is Antares, you can see it's really kind of reddish. And if you guys take astronomy here at UH Clear Lake, you know about the HR diagram, right? Have you ever heard the HR diagram? Except for you. Anybody else that doesn't teach astronomy? Oh, come on, no one's heard the HR diagram? Aaron, he's heard of it. You guys never heard it? You guys taking astronomy? Come on, you never heard the HR?
I spent a week teaching my students the HR diagram, how it applies physically.
Okay, you guys all get astronomy. HR diagram. Okay, when you go to astronomy, you actually teach about HR diagrams. It stands for Hertzsprung-Russell diagram. Okay, so it tells you about all the different stars. It's O, B, A, F, G, K, M.
And don't be a fine girl.
I wasn't going to say that. I know it's going to be a fine girl kiss me, but I wasn't going to say that. Somebody
and don't forget LT, because that includes the brown dwarfs.
That's true. And at the end, they added LT also.
But you can find guy.
Yeah, okay, yeah, there's a thing that goes along with it, which is controversy. I don't know. Anyway, I don't care about that. So this one here is an M1 star, which means it's in the red end of the spectrum. You can tell it's pretty red, right? But what's interesting here is you look at this one up here, and that is definitely not red. That is super blue, right? That guy there, that's Sigma Scorpii. And that is a B1 star. So OB is on the blue end of the spectrum, and M is on the red end of the spectrum of the HR diagram. And you can really tell by looking at this image. That guy's blue and this one's red, right? Does everybody agree that that's blue and that's red?
That's more orange.
It's yellow.
Okay, they're different colors, right?
Yes.
Okay, so not all stars are the same color. And this has how hot they are, and how big they are, and how long, where they are on the, if they're in the main sequence or not, and where they are in their lifetime. Brandon actually taught class in this, so he can tell you all about it.
You're doing good.
Okay, good enough. All right, then there's one more interesting thing here. This is, so we got blue reflection nebula, we got yellow reflection nebula, we got dark nebula down here. We also have this red thing up here, which is an emission nebula. So you see red ones, it's usually all emission nebula. And this is surplus 2-9 here. So this is a very, this is probably another emission as I don't know where it is. So this is a very colorful part of the sky, and the way this picture was taken with a 200 millimeter camera lens and a modified Canon 450D. So it's, you know, it's not a telescope, it's just a regular camera lens with a 200 millimeter, pretty wide area in the sky. It's about a 6-degree field of view horizontally, clearing the sky. These are 4-minute exposures, 38 of them stacked together. This is before I knew about special interferometry, right? Because I did it the old way, all this house and hillbilly drill. And this was taken at the start party. It takes the start party in 2017. So that's this slide that we've been using for our break slide, and that's what this picture is. So I know some of you guys are wondering what that is. It's a cool picture. Pretty easy to take, actually. I mean, I just shot 38 4-minute exposures, stacked them together, and it's actually a pretty easy shot to take.
I like to note that I have, using a refractor one time, actually have seen a yellowish color in that nebula.
Really?
It's
pretty bright.
Yes, it is. So under the right dark conditions, the yellowish color can come out in that region around the Antares.
So how big a scope was it?
It was a wide field, what was it, a 5-inch refractor.
5-inch refractor.
Yeah.
I can believe it, Justin, because that thing's bright. I mean, it's yeah.
And I'm thinking that's more of an emission nebula because of the yellow color, whereas reflective nebula is primarily gray or blue.
The claim is a reflection nebula. The Vandenberg list has it's in Vandenberg, which is all reflection nebula. Yeah. Okay, so
Probably observed as a gray color, but
yeah. Well, anyway, but it's a Vandenberg 107, so they claim that that's a catalog reflection nebula. And there are yellow reflection nebula. You agree with that?
most dark nebulas are because you got a lot of carbon monoxide and frozen hydrogen with silicate grains, and that disperses blue light very efficiently.
It's not a dark nebula, it's a reflection nebula.
No, well, if you have the stars in the right position, a dark nebula can become a reflective nebula.
Okay, I got you.
Yeah.
Okay. So Aaron, I saw your hand up.
Yeah, I just want to know where's the border of Scorpio and Ophiuchus there? 'Cause
Yeah, it's pretty well. This is not necessarily oriented right, but somewhere around here is because this is Ophiuchus and this is in Scorpio because that's the big red star of Scorpius, and so it's probably and it's a jig-jag line. It's like so it's not necessarily a straight line. But this is right. It's right. It's right at the border of those two constellations. Does that answer your question?
yes, sir.
Okay. But yeah, if you're ever out looking, if you got somewhere dark and look at this, it's a cool area, and you guys might enjoy it. Okay. Any other questions about this picture?
Well, one question, forgive my ignorance, but would you be able to visually see or tell me the difference between a globular cluster and a open cluster? Are those the two types of clusters, and can you see it visually from this slide? Is that
Who wants to take that question? This is what a globular cluster looks like. That's a globular, this is a globular, that's a globular. Who wants to tell me the difference between a globular and open cluster and give them a good answer? John.
Well, an open cluster has a lot less stars. You can have tens of thousands to 1 million stars in a globular cluster, and it's packed and very intense in the middle. So if you took that globular cluster, take away the whole intense middle, so all you see is the sparser outer part, that would be like your open cluster.
I'd like to also add that in the globular clusters, they're actually gravitationally bound to each other, while the open clusters they're kind of fleeting away.
Right.
And open clusters are typically newer star formations, while the globular clusters are much older in age, and they lie around the edge of the Milky Way.
Yeah. I'm sorry, globular cluster are actually a galactic halo.
Yeah.
Right. Yeah. So they're further out than say an open star cluster.
you said the open or newer?
Yeah, they're more newer.
Okay.
Yeah.
Interesting.
Yeah, and a lot of the open clusters that we can see are actually closer by. The globulars can be like way out there, 30,000. Light years.
Pleiades is a good example.
They can be way out there.
Cool.
Okay, Dan, you have something you want to add?
Yeah, I'm a little bit facetious, but globular cluster is the Roman legion. An open cluster is an American family, where members of a cluster fly from each other. Never did you see that?
aside from what Aaron said, I find very interesting because, okay, open clusters, this bothers me. They are supposed to form from the same, dust and gas and everything. And then once they form, they actually disperse from each other. They actually go their separate ways, which I think is kind of odd because you think they're nearby and they're associated with each other. They come together. That's always bothered me that open clusters disperse. Anybody got any ideas on? What? Do you know why that is?
Well, I suppose they just don't have enough mass to be gravitationally bound.
Why did they move away from each other though?
That's
Gravity?
You have, well, you have a lot of stellar associations which have a combined gravitational effect because the spiral arms are not uniform in the distribution of stars. It also depends where the where the open star clusters are located. There are a few that are over 1 billion years old, so they can survive multiple orbits. NGC 188 is one of them because it really exists on the fringes of the spiral arms.
So if it's by itself with less of the Milky Way around, it'll stay together.
Yes, and you can see more of the color changes as it gets older.
Does that kind of answer your question?
It certainly does.
Yeah.
Thanks.
Comes on our star parties. We'll have to look through a telescope.
You can see globulars and open clusters.
You can. And
This is one of the most fun things to see in a telescope is the globular clusters. They're really cool.
Any other questions or comments about at this moment? Okay, good. Alrighty.
Now, before we do start party news, I've got one walk-on members minute. Dan, you got a walk-on members minute.
Yeah, I volunteer to a 401c organization named Foundation for International Space Education. Now, they bring 50 of the most brilliant kids in the world from 20 countries to JSC and UHCL for a 15 days instruction in the space program. They work with NASA and their contractors to build a mission to Mars, no less. Incredible kids. And last year, I hosted one of these, an unbelievable young lady from Canada. She had been doing research on the H1 clads in our galaxy, on the VLA. At her age, she was 18 years old, for heaven's sake. At her age, my only research was about the other gender. Amazing young woman. So anyway, I'm telling you this because what we need are good families, particularly families of astronomers, families of scientists, who could host 2 of those brilliant kids for 2 weeks. The only thing you have to do is give them a roof, make sure they don't completely trash the place. You're the parents, okay, 15 to 19, teenagers. That may be requiring some leadership on your part, but for 2 weeks, you have to drive them back and forth to HCL. That's it. If you're interested, come and talk to me.
Okay, Dan, tell me one more time, where are they from?
I'm sorry?
Where are they from?
They are from 20 different countries, all over the world.
20 different countries.
20 different countries, 15 to 19-year-old. And they will come to us from July 16 to the 31st of this year.
July 16th to the 31st.
Yes, sir.
Wow, okay, interesting. Okay, very good. Next up, we have David with Star Party News.
All right. Past events, Fort McCavitt, I believe, was largely weathered out. Doug, you can correct me on that. You guys at least had a decent time.
That's Jerry and the bee. They were there.
Yeah.
Yeah, we saw your picture.
We have 6 people over there.
Yeah.
2 of us, plus Lisa, Ken, and Fred, and Sandra.
I noticed attendance kind of fell off a cliff as the pending weather predictions started coming in for that.
But we had a good time.
That's the important thing. April 1st, we had outreach at Hack Winery. We've got slides for that. April 16th and 20th. Doug's going to talk about the JSC trip to the X-Bar Ranch.
Tomorrow.
Yeah, starting tomorrow. April 28th, end of the month, Friday, we've got another half winery event, Texas Start Party, May 14th through the 20th. And then we've got a couple of events out here that are still in the tentative thing. Doug, did Clear Falls ever get back to you yet?
They are no longer interested as far as I can tell.
Okay.
Yeah.
Can't do any better than that.
Yeah.
All right, April 1st, we had a good turnout at Chris Randall, Reed, Connie, and I, Johnny Todd Zatorsky, Bob Leslie Eden, and Mark and Helen Junko came out with a brand new scope that he just purchased. 6 scopes, 1 pair of binoculars, and about 75 to 80 in attendance. Chris has this cute shirt that he had made. He didn't realize that if he gets it in bulk, it costs less, but he actually just had one made. He brought out his monster. That was quite good. They even started out like it was going to totally suck, I'll be honest with you. But then magically at about 6 o'clock, things started to clear up. The George Observatory even closed for the weekend because they said the clouds were going to be too much. They said nope. And the clouds came in by about 9:15, 9:30, but we were pretty much done with the event by then. But got my meeting over here, Leslie Reed, wonderful little scope that he's got here. Connie and I brought the dog because they weren't sure about the weather. They did feed us, which is always important.
Yep.
The guy just dropped his mark with his new scope that he picked up. Objects were all over the place, M42, Mars, a number of other things were there, plus the moon. Oops, went in the wrong direction. We came out, he was at the last JSC meeting with his little scope. I mean, you got this one of Leslie pointing out a laser pointer to the moon over binoculars. Relatively decent effect. Fortunately, there were no planes in the area. A good wide field area. You could tell, yeah, we were kind of dealing with some sucker holes in the process. And then Reed has this cute little thing down here, because the best I was able to do, at least with the Android, is through the eyepiece this way. This little handy thing at least got me a reasonable shot of the moon here. Obviously, see Clavius, Tycho, this one. Go from there. It's actually a cute little thing. If you want some more information about that, see Reed. And who is the idiot that passed up the chance to call us for the scientist? So,
That's bad.
All right, thank you, David. All right. Okay, so David said, we're gonna go next summer ranch. I've been telling you guys about this for a few months, and it was originally last month, the weather was bad, so now we're gonna go this month. It's actually, Sunday through Thursday, but I'm actually gonna go tomorrow because the weather starts to be good tomorrow. If anybody still wants to go, if you're one of these last minute people that waits the last minute to do things, there's still one cabin available and one RV hookup place. So if you guys want to jump in your car and go to the X-Bar Ranch, you get on their webpage and get yourself some reservations. But it's like luxury astronomy out there. You got a cabin and a bed and air conditioning and heating. You got a big kitchen. You got they got a family room with a TV and a meeting room. It's just really nice. So we're doing that. There's 5 of us signed up so far. All the rest of you guys are missing out because it's going to be fun. But we'll do this again sometime. Okay. Next thing is door. What?
Nothing, I just can't see it.
Can't see what?
Purple and black.
Yes, it's a bad combination, man.
Good thinking there. Okay, so door prizes. Door prizes. Okay, now, you guys, if you normally come to these meetings, you know I normally have a big bucket of stuff with me. But in commemoration of the talk we had tonight, Bruce brought us. I'm doing something a little different. It's like this photon that went to the hotel, and when he came to the desk to check in, the guy says, "Do you have any luggage?" And the photon says, "No, I'm traveling light." I'm traveling light. I don't have any luggage. Oh, and Rick can you come down here and tell us about, Rick brought some things to donate to the door prizes.
Okay.
Can you please come down here and tell us?
I noticed there weren't a lot of door prizes last time I was here, so.
That's true. Come on and tell us about your door prize. This is what they look like. And Rick is gonna come down here and tell us about this.
So 100 years ago, the imagery area over at JSC.
One of the things we were doing, we started scanning all the images and all the mercury, everything mercury on board. And one of the things that we had, which I thought was kind of cool, and I actually made them into giveaways, was we had all the 16 millimeters that had been shot on all the moon missions. And so I told them, I said, go ahead, digitize all of it. And then a couple of them I asked, hey, could one of you go through it, pick all the best stuff, get it down to, 30 minutes if you can. And they actually did a 12-minute one, which I thought was wonderful, only because I like the music better. And then they had a 30-minute one, which is these. And so they took the 16 millimeter, they got it down to 30 minutes of the best. And there were, I think it was 500 hours or something like that of imagery. And believe me, a lot of it was really, really bad. So they picked out the good stuff. A lot of the stuff you'll have actually seen, on some of the TV programs and everything about the moon missions. And they put some really cool music to it. And it's a really fun thing to have. And I had to have, and I found 5, and I know I have more, so I'll probably bring some more. So that, other people can enjoy them. They're just sitting in a trunk in my closet. And so that's what it is. You just throw it in a DVD player, and you go ahead and play it. It's pretty cool. Yeah, if you guys ever have anything you'd like to donate, like astronomy books or something, like donate some door prizes, we always accept door prizes here to give away. All right, so first one is 839. Salsa, come on down here. Okay, you can have a DVD of the moon missions, or a moon map, or a Starliner mouse pad, or a metal Kepler spacecraft. That's one you want. There's Salsa. There's one. Okay, she's a school teacher, so we're always trying to give her things. All right, 831.
Yeah.
Who's that? Oh, Dan, come on over here, Dan. Okay, you got a moon map. You got the 16 millimeter from the Apollo missions of the moon. We have a book called The Plans, which I have no idea what that's about. I know one of you lovely people donated this, so I'm going to say positive things about it. Yes. Okay, you got it. There's that one. All right, give away a couple more here. Okay, 809. Oh, come on down here. Anna, right?
It's very
All right, come on, Anna.
strange because
The first time I came to Washington, actually, I got a flashlight. I think David donated.
I was kind of begging for a chance to get DVD.
You want the DVD? All right, good. Okay, we'll do one more. I'm hoping some of our other new attendees will win something here. 827.
Oh.
827.
That's so cool.
Is that Susan?
That is.
Come on, Susan.
Moon map is CST Starliner, CST 100 Starliner
mouse pad.
moon mission DVD.
All right, very good. Excellent. Okay, so that's about it. Let's see. So next month we're going to be back with the LPI, and hopefully the sound will work better for Trevor over there. So we have some problems with sound on the stream. Makes all at the LPI, the Mystery of the Universe, with Eric Clevenson, which is a friend of yours. Right? He's going to come. So they didn't have guys to keep us in business here. So after the meeting, we're gonna meet you at Monte Pizza, but before you go to Monte Pizza, come on over here and see Bruce's optical bench. Let's look at the optical bench a little bit. And then we get done looking at that, we'll shoot on out to Monte Pizza, and we'll see you all there. Thanks for coming.